So first I give yesterday's remain, and then I use the projector to the second talk. So first of all, here yesterday we proved regression.
근데 저는 불 켜는 게 낫던데.
Here is a statement. So suppose G is a any dimension of affine group. It is R and semi-direct product of GL and R. And then suppose G acts properly on R, then first of all G is at this as a S4. Okay. Here R0 is should be connected through figure, and K is a maximal compact. In G. Is a statement structure of G. If G acts affinely as affinely and project properly on R, then G has this form. And moreover, I forget to say. Moreover, if G is modular, I should say first, but if G is unimodular, it is there exists always discrete uniform subgroup, say gamma inside G. So G over gamma G over gamma is compact. G over gamma is compact. Then and also acts transitively. G acts transitively, that is G to some point of its GP is whole space Rn. Okay, then this also true. R no acts transitively, so R no is R. And one more. That's all. Yeah. Okay. So I'd like to apply this result to the dimension 3. Prime dimension. It is suppose I have this kind of proper transitive group, unimodular proper transitive group. Let's say unimodular. And proper and trust. So suppose you have a unimodular proper transitive group in R3, then what happens? Then we characterize this using the so-called algebra technique. So let me state the result. This one.
So you have R3 or Rn?
Now apply R3.
R3.
So let me state the So the statement is here. First one is so modular first determine the modular transitive group. Modular transitive group G in R3 is other D group. G is isomorphic to vector space R3. One was the D group R3 and nilpotent group, three-dimensional nilpotent group, nilpotent notation N and so on. Yeah. Oh, sorry. Okay. The next is that we restrict to the affine to the Lorentz group. So Lorentz group we usually write down in general in -1, and this is translation part Rn, and this is a Lorentz group. Yesterday I said this, preserving the Lorentz matrix is n -1 plus and -1. So preserving this matrix, so this A and A is again -1. Such a A is Lorentz matrix. So second property, second statement is modular always modular assume modular, but modular next to proper transitive properly and transitive proper transitive.
So unique modular just means that determinant is 1, right? So I never.
Yeah. Discrete subgroup exists.
That's what your definition.
In modular. So yeah.
That's what
Yes. So always this quotient is common. There is some discrete subgroup. And then modular proper transitive. Now this Lorentz group G, that is G belongs to this group. Of course, Lorentz group is a special case of affine group, so such a modular proper transitive Lorentz group G also is actually is one of these, and in fact it is let's say affine is more general than Lorentz. So it not necessarily Lorentz group is always one of these, but this case is true. So is let's see, affine just three groups. So this is isomorphic. No, this is isomorphic to say G. This is okay. This is transient. So stabilizer is trivial. But in this case, it's compact. So stabilizer is in general compact. And here, first case is R3 and SO2, not SO3. This is kind of Weber R3. Probably you can see this R3, so SO2 is 1613 3 by 3 matrix is like that. Okay? SO2. So eigenvalue 1. And or N or S are R. So let me mention, I use later Lorentz group, then this B group N is as the following form. This N all are embedded in Lorentz group is so translation part and then matrix part, linear part, like that. This is two-dimensional, translation group. R2. Okay, so matrix here is identity. So this is two-dimensional, and one more dimension is like this. So theta and then 0, 0, and here 1, 1, 1. So let me finish first. Theta and theta square over 2. So dimension is this parameter x, y, and theta, so dimension 3. And let me note that usually I said, well, this is a Lorentz matrix, and in this case, we change the basis. So in this matrix, this is E1, E2, E3, and the E1 is inner product is -1. Other E2 and E3 are both are +1, and they are also 1. And then in this case, it's not convenient to use this original basis, but instead we took this coordinate equal by this basis. F1, E2, F3. Here, F1 is E1 plus E3 over square root 2, and E2 same, and F3 therefore E3, E1 minus E3, and E2. So this is this F1 is actually null vector, zero vector, null vector, also F3. Using this kind of basis, then according to this basis, the matrix has a form like this one. So this also, you can see this x times F1 plus y times E2 and 0 times F3. So this is important. So what I want to say is because this is trivial identity matrix, therefore this is the translation part is translation. That's the intersection of R3. Translation part is R2. Is R2. So next stop is translation part is R2, but this is of course important. But the translation part is R2, group is R2, is not convenient to make a make this case anyway, proper transitive Lorentz, then no like this kind of compact group come out. But so the next talk, yeah, actually I make this with SO2 compact part come out. Okay. So, but this case center is just one-dimensional center translation. So one-dimensional center. This case is, of course, this is the center. X00 is center, and but abelian subgroup, normal subgroup is R2. So this actually preserves Lorentz metric. And so and this is a measure of I forget to say what is solvable group R. R is this. Also you can write down using coordinate. Fine. So in this case, it's just E1, E2, E3, original Lorentz basis. Yeah. Lorentz basis is this is minus and E2, E2, and E2, E3, E3 inner product is plus 1. So minus 1 plus. And then with respect to this basis, R can be described as follows. Identity matrix and one more. So this is anyway translation subgroup 2 dimension and 1 dimension, or 3 dimension. So 1 dimension more is this theta 0, 0 and here 1. So this is a Lorentz case. So push theta change theta. Theta, push, sense, see. This is a solvable group. This is, you can see that this group is SO, yesterday's notation, this group is SO, SO11. This group is acts on XY as left multiplication. And this is a solvable group. So maybe I should mention R2 is a normal subgroup here. And then semi-direct product of this R. This is the isomorphic to R. Structure is right. And let me mention, this case is also, we can write down R2 and R, but the action is different. But I don't write down because this has only, this has a center R, this has no center, but abelian subgroup R2. So, anyway.
I think that's sort of like the sort of search function.
I mean
the R.
Yes. So minor. And also this is, you can say, nil minor. So the nil minor has also another structure. But they are different by the classification of 3 dimensions. Anyway, so and then one more one. Then here is a classic. Let's consider the quotient of the Lorentz manifold. Suppose next is 3. Suppose n. Now the compact. Now assume compact Lorentz manifold. C manifold. 3 over gamma is this is unfortunately not affine D. Yes, just different. What mean unfortunately means in a compact Riemannian flat manifold is affine D diffeomorphic to torus is some manifold with finite index. So I should say Riemannian case is Tn divided by some finite index. This is f belong to orthogonality. And any compact Riemannian flat manifold is affinely diffeomorphic to this one. This conjugate is conjugate obtained by affine transformation. But unfortunately means in this case, Lorentz case, diffeomorphic, so conjugation is via diffeomorphic. Not like affine diffeomorphic. And then diffeomorphic 2, first is T3, and then F is finite group acting on. You can see RC but secondary product is SO2. So this F belongs to SO2. In fact, Z2. Only Z2. And then next is U manifold divided by delta. Delta is important group. And then I don't mention that how to construct this existence of discrete subgroup, but anyway, because universal cover is either one of these, so divided by this quotient divided by this this notation delta and gamma is this is nilpotent group. That is definition. Nilpotent group is in this case delta is okay. This delta has following central group extension. This is the center. And then quotient is this is of course normal subgroup. Then delta of Z becomes Z2 abelian group. And, this sort of case is normal subgroup is Z2, and then gamma goes to Z. This is style. Okay, so okay, this is so far until here is Lorentz flat case. So now remaining two is next affine group, affine unimodular property. So the number 4 and also 5. 4 is next is unimodular proper terms to affine group. that is G belong to R3. G belong to R3, affine flat group, and then acting properly and transitively. And G itself has a discrete subgroup, discrete uniform subgroup. Is isomorphic here because of the proper not necessarily trivial. R3 semi-direct product of maybe because of the brevity, because of the convenience, simplicity, I assume this belong to special linear group. This is special linear part is GM3R, but I choose only determinant one. So here instead. But we can reduce anyway. As Sanchez said, as determinant is 1. So you can reduce determinant 1 in this case. Anyway. So, not O3, because belong to this, so SO3. And then Heisenberg N is also SO2. And however, solvable cases still are no such a compact group amount. So this is actually Lieber-Bach. This is Euclidean. This case is actually now we discuss using the projector to get the simply transitive action like Heisenberg. Lorentz flat or affine flat is you can get this N Heisenberg group admits Lorentz flat structure also because affine flat structure. But that is transit. If you allow the properness, then this SO2 comes out. And as I said, in this case, previous N, just the center translation subgroup is R2. In that case, you cannot get this one. So you have to change this N. Heisenberg, but change the structure, deforming the structure. But anyway, so this is so finally, this is obtained by Bill Goldman and David Free. The idea is actually same as they classify, finally get the proper unimodular proper transitive action. And then, as I said previously, yesterday, proper transitive affine group is it is so-called amenable P group. And then by Milner's theorem, such a discrete subgroup is virtually solvable, polycyclic. Okay. I should say unimodular. If it removes the unimodular, then this case is G is either virtually solvable or contains the free group in every case. So proper what I said again, proper transitive amenable group is a discrete subgroup of proper transitive amenable group is isomorphic to virtually solvable or subgroup contains free product. So anyway, we are discussing the unimodular case, that is gamma existing gamma and divided by gamma. This is compact, this is unimodular. So this case does not compact. This case is non-compact case. Okay. So the final result, yesterday's final result is this. So it's actually so suppose compact complete finely flat manifold because stress 3 manifold is diffeomorphic. Diffeomorphic to yes. Yeah. Diffeomorphic to torus divided by finite group. This F from 2 because we also assuming the SO3 in general O3. That is okay. And Heisenberg group and delta belong to and same type of SO2. Of course, this is there is a new manifold N of delta, but this notation is delta is not necessarily discrete subgroup in N. Delta belongs to this similar product. So this is called the infranim manifold. So base manifold is infranim means finite cover is nil manifold. That is homogeneous case. And then one more is this Arnold gamma. This gamma is still does not is it this case gamma is just belong to the solvability group. So this is in fact homogeneous solid manifold. I don't write down, but this is infranim. This is solid manifold. So this is the result. Okay. Yeah. So therefore, in each case, fundamental group is virtually solvable. But of course, already proved. It's kind of this is kind of corollary. They proved so-called unimodular proper transitive group, affine group, classify those groups, and then such a portion is in fact these one of these. But different. There are of course lot of distinct different affine flat structures from each. Maybe. That is a modular problem. Okay, now let's start writing and 5 minutes break then.
Yeah. So we can have a 5 minutes break.